Oh, hi there. Thanks for showing up for your learning. It's Grant, the SAT genie, and I'm coming out of my lab today to address systems of equations on the SAT. So these are questions that look like the one we have here, where we have a system of equations or a series of equations. Here we have two equations, and we've been asked to find this magic number k, is what we're looking for. K is a constant, and for what value k is the question that would make this system have no solutions. And it's looking at questions like this and kind of zooming back a little bit that I kind of have sympathy, or I absolutely have sympathy for a lot of people to whom math is not a native language and who look at something like this and say, this is craziness. Like, what am I even supposed to do here? So it helps to zoom out a little bit and understand just like what we're looking at. Okay. And I wanted to start first by showing you how to solve a simpler question type and using that question type to then solve the one that we're looking at. So let's jump down to this one. I have this as a simpler question that we're going to look at. We'll look at this one at the end of the video, which is even more challenging than the one that I tickled you with yesterday. So here we go. We have two systems of equations, and actually, interestingly enough, this question and the previous question are from the same SAT. So same topic, tested multiple times, shows you that these are very common questions on the SAT. There are other questions that involve linear relationships, and these are just one type of those. So we definitely want to master these regardless of your goal score. These are important questions. So here's how we would do a system of equations like this. I can go ahead and look at these and say, I am going to use an elimination strategy. In order to do that, I'm going to multiply the top equation by something that will allow one of these coefficients, these numbers that are multiplying our variables, to match the coefficient in the other equation and have an opposite sign. So I can see 3 and 2. I can multiply by something to get those both equal to 6. So I'm going to multiply the top equation, top and bottom, by 2, like this. And that would give me an equation that looks like 2 times 2x is 4x. 2 times negative 3y is negative 6y. And then 2 times minus 14, that will be equal to negative 28. Because we've done the same thing to both sides, the equation is still balanced. So we're allowed to do that. We're allowed to multiply both sides of an equation by the same thing. And then by the same thinking, we're going to multiply this bottom equation, but there we're going to choose negative 3. Okay? And why are we going to do that? Well, if I do negative 3 times negative 2, I'll get positive 6x. So this will give me negative 3 times 3x is negative 9x. Negative 3 times negative 2 is positive 6y. And then that's going to equal negative 3 times negative 6 is 18. Okay. Now comes the magic, where we solve this system by the technique of elimination. Now what I'm allowed to do is actually add this side of this equation to this side of that equation, and this side of this equation to that side of that equation. Basically, I'm adding the same thing to both sides of the equation because they are, after all, equal to one another, but algebraically, they look very different. So this is where the trick comes in, and we get something that's far easier to solve. I'll show you. 4x minus 9x will give me minus 5x. Negative 6y plus 6y gives me 0, so I don't need to write anything down. And negative 28 plus 18 leaves me with negative 10. That's like a negative 28-degree day that gets 18 degrees warmer, thank goodness. So we're only at negative 10 now. So now I have negative 5 times some number equals negative 10. So that number is 2. But maybe I'm not sure. Maybe they give me more challenging numbers. I'd go ahead and divide both sides by whatever I'm multiplying this unknown by. So I'm multiplying it by negative 5. The opposite of multiply by negative 5 is divide by negative 5. So we're going to do that. Negative 5 divided by negative 5 cancels, and we end up with x is equal to negative 10 divided by negative 5 is 2. Good. So we have x is equal to 2. And now what we can do is take either one of these equations, both will work, and we're going to just grab this and rewrite it down here. 3x minus 2y equals negative 6. And then we're going to go ahead and we say, well, we know x is 2, so let's put that in there. So we have 3 multiplied by 2 minus 2y equals negative 6. So this is 6 minus 2y equals negative 6. Now I want to solve for y. So if I want to find out this y value, I just want to move all the numbers to the other side as quickly as possible. Dealing with the loose addition is best first. So I'm going to first subtract 6 from both sides, and that will give me negative 2y. The sign still comes down. The sign is still part of that number, is equal to negative 12. And then I divide both sides by negative 2. And that leaves me y is equal to 6. Great. And then I've been asked not for x, not for y, but what is the value of x minus y? So let's take that expression. X minus y equals 2 minus 6. 2 minus 6 happens to be negative 4. And there's our answer. This is how you would solve a typical systems of equations question where you're being asked to find the one and only one solution. Now, the hint that I gave you yesterday was parallel lines. So let's go ahead and we'll take a look at this system of equations in Desmos for just a moment. So welcome to Desmos. This is one of my favorite math tools available on the internet. You can find it desmos.com/calculator, or just go into Desmos, a whole host of educational activities, but particularly they have this beautiful graphing calculator, which is very easy to work with. I'll just tidy this up a little bit here for us, make it a little more beautiful. There we go. Okay, so here I have my system of equations, and these I just copied straight from the SAT. You wouldn't be able to do that on the SAT, but working in your studies to practice visualizing these systems really gives you a zoomed out view on what's going on. So we found that x was y and y was 6, and there it is. The x coordinate's given first, and then the y coordinate. And this is what we call the solution to a system of linear equations. This is one line. This is 3x minus 2y equals negative 6. And that's a whole infinite set of possible solutions, okay, that all form a line when they're graphed. And here is the line 2x minus 3y equals negative 14. Also an infinite number of possible solutions. The only one they share is here at 2, 6. So that's what we refer to as the solution to a system of equations. It's the one place in the xy plane that will satisfy both equations. So that's what we mean in these situations. So if we take a look at this situation here, where we have, so now we're going to go back to our other example. And so let's take a look in here. And we're looking now back at the original question. So now we have another system of equations here. Kx minus 3y equals 4, and 4x minus 5y equals 7. Okay? And we want to find this value of k that will not allow the system to have a solution. So here's a really cool thing we can do in Desmos. Let's take a look. So in Desmos here, I can put in, so you see right now, this, if k is 1, then this system will have a solution, right? It will have an intersection point. If I change that and just put in k and add a slider, I get to see what different values of k are going to do. As k gets very negative, then the line dives down. As k grows more positive, you'll see there's one point in here, right about there, 2.4, there we go, where the lines become parallel. These parallel lines will never touch. They will never share a solution. And that's what we're looking for, is this value 2.4. Now, how could we find it without a tool like Desmos that allows me to just look at hundreds of graphs in a couple seconds just by changing that variable? Well, let me show you. If you recall, we changed our equations by multiplying them. So if I wanted to multiply this top equation and this bottom equation so that some of the coefficients become the same thing, I might multiply this one by 5 and this one by -3. So let's do that, okay? And if I do that, I'm going to get this. 5k minus 15y equals 20. And negative 12k, sorry, negative 12x, oops, I should have an x up there. That's kx, not just k. Okay, negative 12x minus 50 plus 15y, my apologies, equals, we'll have negative 21. Okay, if we went ahead and added those equations together, we would get the following. So we would have 5k minus 12x. So it would look like this. I'll do this in another color because we're going to be taking this equation to the other side. We will have 5k minus 12 x's plus 0 equals, and then adding those together, negative 1. Okay, so let's bring this equation down here. 5k minus 12 x equals negative 1. Now, we would like k to be such that there is no possible value of x that can multiply this number and get negative 1. That's what we would like. In fact, the number that k needs to be is whatever number will create a 0 inside this bracket so that the value of 5k minus 12 equals 0. Then we will get an equation like 0 equals negative 1, and there's no possible value of x that will make that true. So that's what we're looking for. And in a second, I'll show you why that is the case. So here, what we're looking for is this value where 5k minus 12 is going to equal 0. Because if this equals 0, then this equation will have no solutions. Okay? And basically what we will have done when we do any elimination strategy here is we will eliminate the y variable, check, we did that, and we will eliminate the x variable so that that's gone. And then we'll end up with 0 equals negative 1, which is clearly not true for any values of x and y. 0 is not negative 1, they are different. So if 5k minus 12 must equal 0, then we can add 12 to both sides to get 5k equals 12, and then divide both sides by 5, and you see it over there, right? You see the answer, right? So k is equal to 12 over 5. There. That is the number that will make the lines parallel. Okay? So that's what we'll do. 12 over 5. Well, we found it was 2.4, but in fact 2.4 is the exact same thing as 12 over 5. They are the same. So that's why we found that in Desmos, but we find this algebraically. Okay? Now, why is that true? Okay? So these systems of equations are being set up this way. Some number multiplied by x plus some number multiplied by y equals some other number. And then we have another equation, some other number multiplied by x plus some other number multiplied by y equals yet another number. Okay? If the ratio of a to b is the same as the ratio of a prime to b prime, then any attempt to eliminate the y variable will also eliminate the x variable at the same time. If a and b are in the same ratio as a prime and b prime, in other words, the two lines are parallel. And that's what we're going to bring with us to this next question down here. Okay. So here is a properly challenging question that I do not believe students will be able to answer if they do not have these skills and these ideas about parallel lines already mastered. Oh, and I don't expect students to master the idea of parallel lines just from this video. This is a walkthrough of how to approach these questions specifically. But to really build the skills to crunch these things, we have a lot of Delta Math problems in my program to get you lots of practice. And these show up so frequently on SAT practice tests that my students get a lot of practice with this. So if I know that if I'm going to use an elimination strategy to try and eliminate one of these variables, if I want this to have no solutions, then the ratio of a to b must be the same as the ratio of 3/4 to negative 1/2. Okay, so that is to say 3 over 4 is to negative 1/2 the same ratio as a is to actually negative b. because there's also a minus there. So there's a minus there, so I can actually say this is positive 1/2 and positive 1/2. The ratio of A to B is the same thing as 3/4 to 1/2. All right. So if I know that, I don't need to know a specific value of A and a specific value of B because it's asking for a fraction here. And fractions are another way to give a ratio. So if A, we could say suppose A is 3/4 and suppose B is 1/2. Then the value of A over B would be 3/4 and in ratio with 1/2. That's the same thing as when we multiply fractions in these cases, we flip this one and multiply. Dividing by 1/2 is the same thing as multiplying by 2. Okay? It's like saying I have 2 chocolate bars. How many half chocolate bars can I divide that into? Well, the answer is 4. Okay? You take the 1/2 on the bottom, flip it, it becomes 2, and then you multiply. 2 times 2 is 4. You have 4 half chocolate bars. So, in any case, this is the same thing as the question 3/4 times 2/1. And that's the same thing as 3/2. Okay? 3/4 times 2, that'd be 6/4 or 3/2. So there we go. That's the answer to this question. And we can get there super fast if we're very fluent with this idea about ratios of A to B in parallel lines. These must be parallel. And we've visualized these things in Desmos. We know what it means for a system to have one solution, for a system to have no solutions, and for a system to have an infinite number of solutions when those two lines are basically different algebraic versions of one another. Okay, they cross at an infinite number of points all along their length. So this is a very fast walkthrough to a very big number of points on the SAT. Like, I cannot overstate how many linear relations questions you're going to see on the SAT and how valuable it is to really be fluent with these, not only to get the points, but to save time for other challenging questions so that you can pick up your maximum SAT score and really maximize your results on this test so that you can open all those doors to the universities of your dreams and have the colleges of your choice opening their wallets to you and saying, please come here and take this free wallet, this free scholarship that's going to give you a full ride. To have your state's education board be gifting you scholarships based on your SAT score. To open up that type of experience for yourself, you have to be a master of linear relations. It's just the basic math questions on the SAT that you must get those points. So I hope that you've gotten something useful out of this. If you haven't, or you still have questions, hit me up by email and let me know what questions I've left unanswered for you. And then I'll reach out and support you in your learning and help you achieve your desired SAT score. Again, thanks everyone for showing up for your learning. Bye for now.